Well, hello again, Woodstock biology students. This is Mr. Brennan. I just want to share some thoughts with you about the sort of next step in the process, how monosaccharides can be combined to create a disaccharide. And if we can understand how that happens, that's the beginning of the chain, but the rest of the chain looks really, really similar. That if we can see how two monosaccharides can be brought together, then we should be able to take two pairs of disaccharides and link those together. And we'd have a molecule that would be 4 units long. And we could take two groups of four and link those together, and that could become a molecule that's 8 units long. Okay, so this is the fundamental combining step, the fundamental bonding that has to happen between monosaccharides. Okay, so let's take a good look at that. So on the left-hand side of the screen here is glucose, a very familiar molecule now to us, right? 5 carbons in a ring, and the sixth corner of the hexagon being oxygen, and then lots of hydrogens and oxygen-hydrogen combinations coming off of the corners, okay? On the right-hand side is fructose, which is also C6H12O6, but there are two carbons that come off of a corner. So here's a carbon to carbon connection here, and here's a carbon to carbon connection there. And so there's only 5 sides to the base of fructose. One of the carbons coming off of the base and kind of flying off one of the edges there. Nevertheless, it's called fructose, but it's C6H12O6. Now, these two, glucose and fructose, are going to come together to create a single disaccharide. Okay, so you see here, they're linked together with this oxygen bond here, fancy name glycosidic bond. And the name of this disaccharide, right, it's 2 units, the name of this is called sucrose, right? And this is really, as I said in the previous video, simple table sugar, okay? So this is the kind of sugar we often put in our coffee or, on various sweeten things various ways, okay? So let's take a look at how that happens, okay? But I do want you to note here that this bond is going to be accompanied by a water molecule. There's going to be the production of a water molecule. It's going to be, a water molecule is going to be given up by these monomers, glucose and fructose. And in the process, that process of giving up a water molecule, that water exiting from the original material is called dehydration synthesis. These molecules, in a sense, are going to lose a molecule of water in the process synthesis, the process of making something new. Okay, so let's take a good close look at that. Well, here we are back at the monosaccharide location again, and I do want you to notice that hanging down below the plane of fructose and below the plane of glucose is this hydroxyl combination, OH for both, right? OH and OH. Now, when these are brought close together, it's possible, right, when these two molecules are brought close together, it's possible for those 2 O's and those 2 H's to recombine, okay? And notice here, what can come out as these things come together is a water molecule can come out. I can take away both hydrogens. You see they're both in red there, right? Highlighting that those are kind of leaving, and one of the oxygens can leave so that we wind up expressing, or the molecules wind up expressing out one water molecule, but leaving behind the single oxygen, right? This one black letter oxygen, black letter O right there, is the oxygen that remains to combine these two together. That process, as we said just a few moments ago, is called dehydration synthesis, the expression of water out of this combination of molecules, right? Leaving behind the O as a glycosidic bond, okay? So just before we let go of this, right, let's remind ourselves, where did it come from? There were 2 OHs, an OH hanging down below the glucose and an OH hanging down below the fructose. And you see there are different OHs in different places. There's one over here and one over there, another one here. Fructose has a couple of OHs that are hanging down. So there are these different combinations, and that may actually impact the way in which glucose can bond with other of the monosaccharides, okay, others of the monosaccharide family. All right, let me show you what those things look like, okay? Here we go. All right, so don't be frightened by this picture, okay? Here's sucrose. It's glucose on the left, fructose on the right, and we just showed how that oxygen bond can be left, right? Left behind when the two OH groups combine to create this oxygen and water, right? Now, what if you had galactose and glucose? So the glucose here is in this kind of, I don't know, yellowish orange, if you will, and the galactose is in this kind of pale green. And notice again, here's this oxygen bond, yes. And one key difference, right? Galactose is a hexagon like glucose, but it looks like there must have been an OH group that was above the plane that combines with an OH group that was below the plane of the hexagon for glucose. So the above the plane OH group on galactose and below the plane OH group for glucose combine to leave behind the oxygen and press out a water molecule. So same chemistry, if you will, the same combination of elements, leaving behind an oxygen bond, connecting the two of them together. And then if you have two glucoses together, all right, you'll get an oxygen bond happening here and an expression of water, okay? And the only difference between the glucose between the maltose and the sucrose, let's see if we can see it. It looks like here, this from the glucose up here, there was an H above and then an OH below, and then there was an OH below here that was below some complicated collection of carbons and hydrogens and oxygen. Okay, so it looks like that combination of carbons, hydrogens, and oxygens is in a different vertex, and we're just connecting to a different corner, if you will, so that you've got these two hydrogens above the plane that are left over. That's not really terribly important, but it's an interesting thing, I think, to notice. And I want you to recognize that, like in every single case, right, whether we're connecting glucose to fructose, glucose to galactose, or glucose to itself, the dehydration synthesis occurs, leaving behind an oxygen bond to pull the two of them together. And let's just take one moment to think about, if that's the way that the disaccharides come together, how do we get long chains of disaccharides? How do we create polysaccharides? Well, let's go to our previous picture here, right? Here's the creation of the single disaccharide. And I would like you to notice, right, there's an OH group hanging out over here on the far side of this, fructose molecule, right? And if we go to the far left, there's an OH group hanging out on the edge of the glucose. And imagine this doubled up, right? And this one on the left-hand side getting matched up with this one on the right-hand side, so that this sucrose molecule could be bonded to another one right here, right? And in the process, it could create one more glycosidic bond with a water molecule being expressed again. So we could create essentially an infinite chain by continually connecting OH groups to OH groups, dropping off of water and leaving behind an oxygen. Okay, so I hope you can imagine a long chain like that. All right, thanks very much, and take care.